Calculating the pH of a weak base solution. So weak bases in the Bronsted-Lowry sense are proton acceptors. And they're distinct from strong bases. In the strong bases you should be familiar with are the alkali metal hydroxides and the heavy alkaline earth hydroxides, calcium, strontium, and barium hydroxide. But weak bases only partially ionize in solution. And what a weak base will do when you put it in water is it will undergo what's known as hydrolysis. And hydrolysis simply means the splitting of water. So for instance, we have ammonia, which is a weak base with which you should be familiar. And I'm going to go ahead and I'm going to write the reaction that ammonia undergoes when you put it in water. Now, when you're doing these weak base calculations, you really should include water in the balanced chemical reaction because, to be honest about it, the chemistry doesn't make any sense unless you put water as one of your reactants. What's going to happen is that the weak base ammonia is going to accept a proton from water and leave behind the hydroxide ion when it does that. So now we have our two reactants, ammonia and water, which is a pure liquid, and NH4 plus and hydroxide ion. We'll use the same technology, the ICE table, that we used for weak acid calculations, only in this particular case, we're going to solve for the concentration of hydroxide rather than the concentration of the hydronium or hydrogen ion. So in our problem here, we have a 0.100 concentration of ammonia. We don't particularly care about the concentration of water because it's always constant at approximately 55 molar. We have no ammonium ion and no hydroxide ion initially. Our change will be minus X for the ammonia and plus X for the ammonium ion plus X for the hydroxide ion. At equilibrium, we add the initial in the change line and we get 0.100 minus X, and then 0 plus X is just X plus X. So that should look very familiar, but again, I want to stress to you, when you're writing your balanced chemical reaction for weak base calculations, include water because the proton that ammonia accepts has to come from water. That's what we call the hydrolysis reaction. We'll go ahead and set up our equilibrium constant expression, which is going to be Kb this time, not Ka, and our two products will be NH4 plus times the hydroxide ion concentration. And then we'll divide that by our reactant, which is our base ammonia. Why don't we put water in the denominator of our equilibrium constant expression? Because we never put pure liquids in the equilibrium constant expression because they don't change in concentration. Only components that can change in concentration go in the equilibrium constant expression. And that's either aqueous solutions or gas phase components. So now that we've assembled our equilibrium constant expression, we want to see if we can simplify our math so that we don't have to employ the quadratic formula. And the way we're going to do that, just like in the weak base calculation, we're going to examine X relative to the starting concentration by comparing the initial concentration of ammonia to the Kb for ammonia. And we see that the Kb for ammonia is very small, 10 to the minus 5. What this indicates to us is that ammonia will not do a great deal of hydrolysis. It will only be to a small degree, so much so that since there is the Kb is at least 1,000 times smaller than the initial concentration of 0.1 molar ammonia, that we can ignore this X will be small enough that the resultant equilibrium concentration of ammonia will be very close to what it is right now. But we should check once we get to the end of our calculation. So what we're going to do now is we're going to go ahead and plug in our values with our simplified math. And the Kb for ammonia is 1.8 times 10 to the minus 5, which is equal to, from our ICE table, x times x, which is just x squared, divided by 0.100. And again, if I had the minus x there, that would result in a quadratic, and I would have to use the quadratic formula to solve that. So we'll check it at the end to make sure that our assumption is valid. So we're going to go ahead and solve for x. We'll multiply both sides by 0.1, so that'll be 1.8 times 10 to the minus 5. And that's just going to equal x squared. We're going to get rid of the squared term by taking the square root of both sides of the equation. And when I do that, I wind up with an x value, which is equal to the hydroxide ion concentration, which is equal to 1.34 times 10 to the minus 3 molar. And that is our hydroxide ion concentration. From there, I can get the pOH by taking the negative log of the hydroxide ion concentration, which in this case is 1.34 times 10 to the minus 3, which gives me 2.87. Now, I'll tell you this, that if you stop right here and on a multiple choice test, you're going to find that answer, but you have not gone far enough to get the correct answer. If you'll remember, pKw, that's the negative log of the Kw for water at 25 degrees, is equal to 14. It's equal to the pH plus the pOH. So we can get the pH by subtracting the pOH from the pKw, which is 14 at 25 degrees. So that's going to be 14 minus 2.87, which winds up being 11.13. So that's our pH, which makes sense since it's a base that we're putting into water. You wouldn't think that you would get an acidic solution if you put a base into water. You should get a pH above 7, and this is above 7, but not so much above 7 that we would think of it as a strong base. We want to go ahead and check our percent ionization by taking a look at our X value, 1.34 times 10 to the minus 3 divided by 0.100 times 100. When we perform that calculation, we wind up with a percent ionization of somewhere in the neighborhood of 1.3%. We use the same 5% rule as long as we're under 5%. Our assumption that X relative to the starting concentration was small enough to ignore is valid.